All right. And this is, I think, our final set of slides about diffusion and applications, which is contrastive language audio pre-training that I mentioned a second ago. So what is CLAP? And so we start with CLIP because that was our kind of basic reference. What CLIP does, it actually takes two different media types, okay, or modalities. In this case, it's text and image. Uh, has some kind of representation, has to be in the same space. Okay, so we use a text encoder, image encoder. And the whole idea of contrastive learning is actually to pair correct matching pairs, so that the image with its correct annotation would be the ones on the diagonal here, while the others, which are the incorrect matchings, will be off diagonal. And the whole idea is now to train another neural network that will try to shift these original embeddings into a new space where these will be close by, while the incorrect matching, the incorrect pairs, the non-matching pairs will be far away. So in CLAP, we kind of did the same thing using text encoder and audio encoder. And that's what, made CLAP being so popular, because now you have this joint embedding between descriptions of audio and the actual audio signals. You can use this now in various ways, not necessarily for synthesis. You can use this for, let's say, classifier. How would you use a CLAP for classifier? Well, the idea is, let's say you have specific classes that you want to now divide your data into these buckets: dog barking, rain falling, siren, whatever. You actually, using the text encoder, can have these labels as embeddings. Okay. Now you take your testing audio, you generate your new representation of audio in the same contrastive space as A1. And now you start matching this against all of these labels. And the one that actually matches best will be your decision. So kind of using CLAP, we get zero shot, or we get a classifier for free, okay? Just because now if you define your buckets without training any encoder, and then seeing how your signal, okay, or audio in this case, falls into these buckets, you will take the one which is the most probable, and here you go, you got a classifier. So in the contrastive, our paper, with Getjan as the first author, he graduated from UCSD last year, and there are little, not little, but I mean, there's some important details that try kind of to make CLAP work, not only the amount of data, but also treating short sounds, long sounds, averaging them using feature fusion, and so on, comparing this to different possible text encoders, and also the audio encoding itself, of course, matters. So the audio encoding is done using another work by Kea, which is the HDSAT, that actually using an audio transformer, which is a version of one of the visual transformers. And I will not go into the details of how it's done, but very roughly, it basically takes a spectrogram, does some kind of raster scan, and then breaks this into tokens. And then these tokens are ran through a sequence of transformers that reduce slowly the dimensionality of the output. That's why it's hierarchical, until you have an output. And this was trained on sound event detection. So this is a pre-trained transformer for sound event detection. But once the training was done, we just now use this HDSAT as a representation, as an embedding. Okay. So here's the reference to the paper. And using this, and then using HDSAT, applying this to applying contrasting language or contrastive method to this with language, and comparing this to other methods, okay, we actually have the best performance on different data sets and different representations. Okay, so comparing this also to audio classifiers, which are dedicated, there is it's available, okay, on the web. So that became a very popular method of analyzing audio. Now, how we actually use this for generating audio, for generating music with our latent diffusion model for music. So the whole idea is that now you have audio waveform, you have text. You can use this clap to decide which of the representations you want to have. And this is analyzed into a spectrogram or MEL spectrogram, and then actually we use a latent diffusion model. So not only a spectrogram, we use a pre-trained variational autoencoder and trained a diffusion model on these VAE representations, which have to be decoded using another method. So the hi-fi again is the decoder here that was trained on these representations. And the options are, you can basically use either a sound or text as a prompt into a diffusion model. So this diffusion model now will be triggered with noise, and it will be guided. And in this case, it's film concatenation. It's not a cross attention like you've seen before. And I will not go exactly, what this feature um, film stands for, feature linear modulation. I think I'll have to check. But how this method, which is really a linear combination of the vector and the features, is imposed on these latent states of the diffusion. Now this becomes the guidance. Okay, so here we go. We can now have an audio prompt and generate similar new audios to that audio, or we can have a text prompt and we generate a lot of possible versions of audio that correspond to this text, same as you would do in images. So we have this text to music model design with a lot of different options. Okay, you can go from text to audio. Okay, so going through this process, that's kind of a different summary of the same thing. You get a cat mewing, then screaming, and so on. So you have this text prompt, and it actually guides the latent diffusion that was trained on these VAE encoder decoder steps. So this is exactly the previous one. It can be also used for in-painting. Okay, so you can see that you can basically encode something with missing data, and it will complete. Well, actually, I think the better name is outpainting here, where you can kind of go and use these things as a completion of missing audio. You can do also a style transfer where you basically want to impose, a specific text, okay, on the latent diffusion that is also guided with initial audio. So if you want to explore this music LDM, here references to the original implementations, and I would also suggest trying. It's a fork by Tornike, who is our graduate student, and it gives you this nice textual interface where you can also play a little bit with the parameters, with the guidance scale, how many examples you want, how many candidates, and so on, to do these manipulation, synthesis, style transfer, and so on. Okay. Now, I think I kind of mentioned already this, so I will skip this. Just kind of, again, text to music, music to music, and style transfer, just represented maybe a little bit more graphically in a nicer way. And maybe as a little finale, I can show you some ideas of creative use or compositional use of diffusion. So one of them is, well, can you use, let's say, poetry, okay, and create songs with poetry? Now, I know that with Udio and Suno, today these things are done with specific genres as complete songs. When we did this, I mean, Refusion was there. I don't think the Udio, and maybe at least I was not aware of, but they were still not to the level of popularity and performance that they are today. So here, the question was how you would translate this to meaningful prompts in terms of music, because this is a very poetic text garden. The gardens are not the same all the time. There's a slow decay from yellowing to yellow. So how actually you would translate this to music? We didn't train this on actual songs and poetry. That was kind of unrelated. We have the music diffusion model, and we have poetry. So the idea was to ask actually ChatGPT to go and give you the musical prompts for these songs. So that was the aspect of trying and rendering a very abstract text metaphorically into music LDM and eventually create the song. Um, a couple more examples in a second. So the next one, okay, I jumped out of the presentation view. Yeah. Another example with sound poetry. Um, so uh, Jaap Blanc, he is a sound poet, a very famous one. He actually composes these texts, which are sequences of very abstract, symbols. Could use ASCII, could use other descriptions, and basically it's a gibberish that create poetry with a specific intent. So if you're not familiar with sound poetry, it's really a fun process. We have some links here to the performances, and the idea is here are his poems. Okay, as bizarre as it might look, this is an actual creation and performance that sound poets do, and Jaap Blanc is really one of the top um, sound poets. Uh, Now, how would you interpret this? He actually reads this out with a specific kind of interpretation intent. ChatGPT gave us this interpretation that would be the music imagery for this text. So every verse had its own rendering. The first one, mysterious, ethereal piece. Another one, electronic textures, electronic beats. So we do use a lot of the existing mappings. Also, when we did clap, we used existing pre-trained LLM models on text, and then we combine them and generate a bank of audio clips. So we actually used uh, music LDM to create a lot of examples. We load them to Somax, which is something we mentioned in our lecture notes when we spoke about the shallow methods, the VMO, Somax. There was a lecture about Somax. And then when we created these clips from sound prompts, we use Somax with the audio, with the singer or Yap's voice to kind of trigger specific clips as an accompaniment. So I don't know if this will work right now as an example. Okay, so unfortunately, yeah, it doesn't seem to going to the right link. Oh, maybe okay. So here's the small recording of that performance with these encrypted poems. Let me just make sure that our sharing is sharing audio, share sound.
Mr. Shlomo Dubnov has done deep research into converting text into sound and music by artificial intelligence. He showed us on Friday what he did with the poem of Rilke. When we were asked to do something, present something here, I thought, why not send Mr. Dubnov a sound poem and see what he can do with that. And I think it came out really nice, and the sounds are here being put through so much by George Bloch, and I will read the poem entitled Five Encrypted Proposals for Cinq Propositions Encryptées.
I think I gave you an idea. I hope the links work on the slides that I will post online. So another use of this is actually connecting images to music, but not specifically like any image, but we use so-called graphic scores, which is an experimental way of notating music. This is actually a description of musical piece. Cornelius Cardew was an experimental British music composer. He wrote this book called Treatise that has 173, I believe, 306 of these score pages, and they're given to musicians for a very kind of imaginary interpretation. It doesn't really have any fixed musical meaning, although it does seem to use a lot of notation that reminds you of music. But people meet, they discuss how to interpret this music, who takes what role, and then actually perform this. And every performance is very different. So we thought, well, why not ask ChatGPT to do that? The visual version of ChatGPT, the O4, with our musical LDM and generate these musical examples of renderings. So the idea was, again, take a graphic score, create a description of what every score might mean. We actually divided the score into segments, and then also added maybe some prefix saying what kind of sound we want: sine waves, string orchestra, experimental. And we did this outpainting or inpainting, what I called before, but this is kind of outpainting, and then generated a continuous version where the previous segment was used as a context and then the new one, and the prompts kept changing, and improvise the audio. So, I don't know if we have time to demonstrate any of them. Maybe just kind of as a short lecture. So yeah, you can kind of now imagine some uses of this as a creative way to generate something which is not specific to any style, and very abstract renderings or installations, experimental music, and so on. So let me skip. Yeah. Yeah, I was kind of imagining creative diffusion assignment, but we eventually decided not actually to make this into a graded assignment. But if anybody wants to try this out, there is this collab that actually implements that treatise uh, um, framework. Okay, and you can generate music from graphic notations. You will need a text file with a descriptive sentence per line, and then you can generate this from a ChatGPT, from a graphics core, and then run this notebook and have your own compositions. So yeah, you're welcome to try this out. Also, if you have any other ideas, suggestions of how, different, basically agents, right? We come to a point where we have multiple agents. Also now, some of the work we're doing is on multi-track diffusion, so you can have diffusion that learns multiple instruments together, how they depend on each other. Uh, I think this pretty much is the end of the diffusion class and the presentations. And yeah, if you have any ideas that are interesting for you in this topic, again, as I said, we add this year because this is really one of the more exciting fields of investigation, also conceptually. And yep, projects or any interest, you're welcome to contact myself or our TA, either for the projects at the end, or as a general interest, maybe for future research. Okay, well, thank you, and yeah, I hope you enjoyed the diffusion models, or diffusion, the theory and the models of diffusion as applied to music. And yeah, see you in class.